Okay, let's get started, please. Okay. So, so I'm going to start off with actually an advertisement or commercial for Math 139. That is a course that I hope to teach next year. So this is the Fourier Analysis course. So I don't know if it'll happen or not, but I'm hoping that next year that I'll teach a course in Fourier Analysis. The prerequisites for the course are this course. Okay. So I haven't been able to teach the course in several years, but anyway, I'm hoping to do it. So yeah, so I was digging through my desk this morning. I found the old commercial, basically, that I would give that I gave the last time I tried to run the course. Okay, so here we go. Fourier analysis is important. In fact, it is ubiquitous. It is all around you. How do you hear? How is sound translated into electrical signal? In fact, your ear does Fourier analysis and is doing Fourier analysis right now. It actually occurs through the cochlear membrane. Like the vibrations get translated into sound via something that is sort of like Fourier analysis. Actually, that is a lie. It's not Fourier analysis. It's something called wavelet analysis. Okay, it's something called wavelet analysis, which is a descendant of Fourier analysis. Okay. Fourier analysis is also used in image compression, sound compression, basically any sort of data compression. It is used in it is the mathematics that underlies CT scans. It is used in radar imaging, used in linguistics for speech recognition, etc. For those of you who like pure math, those of you who like pure math may be frowning with disgust. But let me add that it is also inextricably intertwined with complex analysis, PDEs, number theory, and etc. What does Fourier analysis have to do with? I'm giving a commercial. What does Fourier analysis have to do with? Well, light. Other than light. Well, you start with the following question, right? Given an arbitrary function on negative pi, right? Can we express f as some combination of waves, right? As some combination of waves. Negative, positive. Okay. So the answer is, as it almost always is, no, we cannot. Okay, but then you ask, if the answer is no, for example, you can have a continuous function whose Fourier series, this is called the Fourier series, doesn't converge back to the original function. But then the answer becomes, the question becomes, to what extent can we do it? To what extent can we recover our function from the Fourier series? Is it possible to make this work? Right? Is it possible to make this work? In what sense does this actually work? Okay. Okay. This Fourier series has applications to partial differential equations. There's a kind of cool application in the book that I want to use called the isoperimetric inequality. So isoperimetric inequality, which says the following, that if you have a curve, and the curve is you have a curve gamma, and the length of the curve is L, okay, and it encloses a region A, then the size of that area is controlled by the length squared over 4 pi. Okay, so this is the isoperimetric inequality, right? Saying that that there's a relation between the area enclosed and the length of the curve, and further that equality equality occurs if and only if A is a circle, gamma is a circle. Okay. And that turns out to be an application of Fourier series. Okay. So there's a second part where you ask if you have some function from R to R. Okay. You have some function to R to R. Can you express f? Can you express f as again a sum of right? So these guys, remember, were what we call the Fourier coefficients. Okay. So you know, can you express your function as some linear combination of these waves? Can you express your function as some combination of some sort of continuous version of the Fourier series? So this is like a continuous version of this. Okay. Okay. And this thing is called this thing here is called the Fourier Transform. Right. So the Fourier Transform, and this has applications in PDEs, and also to the Radon transform. So the Radon transform is what happens when you have some function. You have some function on the plane, okay, and you're given information about its integrals over lines. Okay, you know the integrals of the functions over lines on the plane. Okay, you don't know the actual values of the function. All you're given is this information of integrals over lines over the plane. And your question is, are you able to recover the actual values of your function, right? It's sort of like a game of magic square, right? Where you've got this matrix, and suppose you know the sums of all the columns, sums of all the columns, and sums of all the rows. Can you figure out the actual values in your magic square, in your square, right? So this is like an ultimate version of that, right? Right? And this is exactly what people do with CT scans. Okay, this is what is done with CT scans, almost. So with a CT scan, you have a human being. Everybody laughs when I draw my human being.
So there's a cross section.
Yeah, it's a cross section. Yeah. The first time I did it, I was like, so you have this human being, and everybody cracked up. It's a cross section, right? Okay, you have a cross section, right? And so you what happens is you shoot the X-rays through, right? You shoot the X-rays through, and then the value of the attenuation of the X-ray gets recorded on the other side, right? Like how much the intensity of the X-ray has decayed is on the other side, right? Is recorded on the other side. That basically gives you an integral. That gives you an integral over that ray through the human body. Okay, so you run this thing through, right? And if you've ever been through the CT scan, the thing spins around you, right? Like what's it doing? Well, it's sending this thing around so that it can take X-rays from many angles, but not all angles, because if they did, you would die, right? Right? If they did it, if you actually had every single angle, then that would require an infinite amount of radiation. Right? Right? Okay, so they do it from some angles and then they approximate, right? And using the Radon transform, they invert the Radon transform and then figure out what the values are at every point, basically at every point on the inside, right? And they do that, allowing you to reconstruct a three-dimensional picture of your interior. Okay, so yeah, and the proof of the inversion formula for the Radon transform, well, it involves the Fourier transform. Okay. There's a third part of the course, which is about functions on groups. So you have a finite abelian group. those of you who've been through 171 know what this is, know what this means. But anyway, you've got some function on a group, and you have this thing called the dual group, G hat dual group. So this is for people who've seen these terms before. The dual group consisting of all homomorphisms from G to the circle group. Okay, from G to the circle group. Okay, and so these guys we denote by little e's, and the question is to express your function. So your function is on the group now. This G is in the group. You can express your function on the group as a sum of coefficients times these elements of the dual group. Okay. So as E runs over the dual group, you can actually recover you can have some sort of analog of this inversion formula. Recovering your function by taking sums of these guys, sums of these waves. You're recovering your function by taking sums of these waves. They're not really waves, but yeah. Okay. Okay, and that part has applications to the fast Fourier transform. So very concrete applied applications, and the course finishes up with the proof of Dirichlets there. So it goes from this stuff, the Fourier analysis on finite abelian groups, to and uses that to get the proof of Dirichlets theorem, which says that if you have Q and L that are positive, relatively prime integers, then there are infinitely many primes of the form L plus KQ, where K is some integer. Yeah, so this was a kind of a masterpiece of the 19th century number theory, and what I hear is that Dirichlet, a number theorist, happened to hang out with the analysts, and so he learned about Fourier analysis and stuff, and so he was able to get this result in number theory that had stymied everybody. The proof of this is incredible. The last time I ran the course, it took me 4 lectures to do just this one proof, for 4 days. Yeah, it was great. Okay, like what could be better? Yeah. Okay. So the text is by Stein and Shikarchi. Stein and his graduate student, his PhD student, Shikarchi. Stein is one of the great analysts of the 20th century. At the basically when he was in his 70s or something like 70s or 80s, he decided to write a series of 4 books that would present analysis in an organic way. So he's got Fourier, complex, real, and functional analysis. Right, and Fourier is the first one, and everything that follows sort of links back to it. So he's created this, instead of presenting the fields in isolation, he's got this thing, very unified presentation of analysis. It's amazing. Okay, so I can count Stein as in my family tree. He is my advisor's advisor. So yeah, not that I have anything to do with Stein, or even with my own advisor, but yeah. I actually only took one class from Stein over the summer at a summer school in number theory, actually. Yeah, so Stein was at Princeton, but I never took anything with him. Yeah, but anyway, so I'm not really close to Stein. I'm not close to Stein, but all this stuff is, I'm very familiar with the style and stuff. So yeah. Okay, so yeah, so to end my commercial, this class is, of all the courses I've ever taught, this is the coolest class. So if I manage to teach it in the future, I hope you guys can take it. Maybe even as cool as topology. Okay. Okay. So, and a commercial. Yes, Mitchell.
Have you ever taken a class taught in the Moore method?
No. Yeah. So I don't know if you've heard of the Moore method. It's basically the professor doesn't tell you anything, but just breaks the material down into bite-sized bits. So, like, put up the definition of something, and then put up a simple fact, and say, okay, everybody, think about this fact. Right, and then prove this fact, and so it's everything is proven by the students. Nothing is done by the professor, basically, except breaking it down into this bits, which is not so simple. Okay. Yes.
So you're not teaching it next semester?
I'm not teaching next semester. Next semester, I'm just teaching the computer science class. Yeah. I only teach one upper division course a year, so I wouldn't be teaching it this year no matter what. It's most likely that I'll try to teach it in the spring of the following year, in the spring of next year. Okay, half an hour to give you some sense of what this thing is about. It's a little bit tricky. What's that? It's not going to be on the final. I'm sorry. I know you asked this last time, Laura, but I was so worried that if I said it's not going to be on the final, nobody would show up.
Wait, so the last time's material won't be on the final?
No, it's not going to be on the final. No. Okay, so sit back and enjoy. Sit back and enjoy.
We're not really taking notes.
You probably learn more this time. Sorry to make you worry. Okay. Yeah, I just knew that if I said it's not going to be on the final, there'll be nobody here, right? Then nobody here. How do we take a class picture? So I brought the camera so we can all take a picture together. Okay. Yeah. Okay. So, right. Let me sort of start from the beginning in some sense. Right. So you've got some function, right? And it's not. I'm gonna do it on the interval negative pi. Okay. So that the equations turn out to be a little bit. The expressions turn out to be a little bit simpler. Okay. So then we've got this thing. So for each n in the integers, we define f hat n as the integral 1 over 2 pi from negative pi to pi f of x e to the negative I n x dx. Okay. So last time I wrote this as e to the negative 2 pi I n x over L, but now L is 2 pi, right? L is 2 pi, and so we get the expression is a little bit simpler. Okay, so these guys are called the Fourier coefficients. Okay. These guys are the Fourier coefficients of your function, and then we take those guys and we take those Fourier coefficients and we multiply them by e to the I n x, and we take the sum from negative infinity to positive infinity of these guys, and this thing is called the Fourier series of f. Okay. And like I said, there's no guarantee that this thing converges, or that even if it does converge, that it recovers your function. Right? In fact, as we said last time, right, it's futile to hope that you could recover it pointwise, okay? Because you can have functions that have the same Fourier coefficients, but that differ at a finite set of points, at a set of points of measure 0. So that's hopeless. Okay. So why does this make sense? Why does this make sense? Well, one defines an inner product of two functions as 1 over 2 pi. So you've got these two complex valued functions on negative pi pi, and you define an inner product on it by taking the integral of one against the complex conjugate of the other. Okay, the integral of one guy against the complex conjugate of the other. Right. So, right, if you take e to the I n x and you take the complex conjugate of it, well, that turns into, let's think, this is cosine nx plus I sine nx. Right. When you conjugate it, well, you get a negative here, right? So you get cosine nx minus I sine nx, right? So you get cosine negative nx plus I sine negative nx, right? Because the sine is an odd function and the cosine is an even function, right? And so when you conjugate one of these guys, you get e to the negative, right? E to the I times negative nx. Okay, so the complex conjugate of these what are called characters is another character from the opposite side. So what we're doing here then is this Fourier coefficient is really f against e to the I n x. Right, we're taking the inner product. Right, we're taking f against e I n x bar. Right, this guy is e I n x bar. Right, in other words, we're taking the inner product of f against e to the I n x. Okay. Okay, and you notice that if you take e to the I n x against e to the I m x, well, what's that going to be? That's going to be the integral 1 over 2 pi, negative pi to pi. You get e to the I n x, e to the minus I m x dx. Right? You've got e to the I n x, e to the I m x bar. Right? Okay, well that's just 1 over 2 pi, negative pi to pi, e to the I n minus m x dx. Right? Okay, but this function is 2 pi periodic, so you get 0, right? So this is going to be 0, right? Think of what this thing is, right? This is cosine something x, plus I sine something x. Well, that's 2 pi periodic, right? So so when you integrate it, you get 0, except when n equals m. Right? When n equals m, then you get 1. Right? So you integrate 1, you get 2 pi divided by 2 pi, and the integral turns out to be 1. Okay? So what you get 1 if n equals m, and 0 if n differs from m. Okay? So you've got these functions, and they are perpendicular to each other. Right? They're perpendicular to each other, and if you take this thing against itself, you get 1. Right? As you might have seen in linear algebra, right? If you have an inner product, you can define a norm. Right? The norm of f is defined as the square root of the inner product of the function against itself. Right? And so these guys are all norm 1. Right? Because the inner product against itself is going to be 1. Right? The square root of that is also 1. Okay? Okay. So what do you have? these guys, right, these e to the I n x, as x n ranges from negative infinity to positive infinity, are orthonormal, right? They're orthonormal. You know, again, go back to linear algebra, right? They're orthogonal to each other, and they all have norm 1, right? They're orthonormal. It's an orthonormal system, okay? And so, right, what do you do with an orthonormal system, right? You hope that you can express your function as a linear where am I? You hope you can express your function as a linear combination, right? As a linear combination of these vectors, right? Right? You've got, you know, let's think of them as vectors, right? You've got these vectors, they're all norm 1 and they're perpendicular to each other, right? You probably remember, right, that if you have an orthonormal basis, right? If you have an orthonormal basis, then, right, you have some vector and you express it as, let's say you have an orthonormal basis b1 through bn, finite dimensional space, say, right? And you want to know, like, so V is summation Ci Vi, right? You take some vector, and it's going to be a linear combination of the basis elements. How do you find the coefficients? Well, if you recall, the Ci turned out to be the inner product of your vector against the appropriate basis element. Okay, so that's all we're doing here. That's what we're doing here, right? We're taking, we're wondering, we are wondering, is f really summation of f e I n x as n goes from negative infinity to positive infinity, right? Right. We're basically trying to ask: is this thing really some sort of orthonormal basis? Right? Is this thing an orthonormal basis for our space? Okay. Right. If so, then we should be able to somehow. We have to deal with the fact that it's infinite, right? We've got infinitely many terms here, so it's not a finite dimensional thing anymore. But in some sense, is it true that you can recover your function from this expression of it as a linear combination of these waves? Okay, and so this is Fourier's original idea from 1798 or something like that, and nobody believed him at the time. Right? They all thought that this is no way possible, and in some sense, it's not possible. But the whole of Fourier analysis is to think about to what degree is it possible, in what sense can it be made possible. Okay. Okay. So now is when we get a little bit crazy. Okay. So. Okay, so let me start off with the dumb and not dumb questions from last time. So we have the Dirichlet kernel. Right, with Dirichlet kernel, d sub n x, defined as summation n equals negative n to n. Oh, Abel, you have to leave. Okay.
The picture, yeah.
The picture, yeah.
I wanted to be here, but
I'm sorry, I
No, it's fine, it's fine.
should have taken it.
We can.
We'll
Photoshop
Photoshop you, I'll do that.
Yeah. Like, it floating in the air or something like that.
Maybe you can also send us the ones from your iPhone on Monday. I think
Yeah,
it was here for that.
yeah, he was there for that, sure. Okay. I should have taken it. Okay, so e to the I and x. Okay, and we have this thing, the Poisson kernel. Poisson kernel, PR theta, defined as summation r n e to the I n theta, and from negative infinity to positive infinity. Okay, and that, when I asked last time, what are the Fourier coefficients of d sub n? What are the Fourier coefficients of d sub n? Okay, so you should think, well, the Fourier coefficients of d sub n should be the numbers that you use, should be the coefficients that you use to express this thing as a linear combination of the EI and X, right? But this thing is already a linear combination of the EI and X. That's why this was a dumb question, okay? This thing is already a linear combination of the EI and X. It's a finite linear combination of the EI and X, right? So what are the Fourier coefficients? Well, you see what they are, right? Right, so if this is n, we're talking about the Fourier coefficients. We're talking about its Fourier coefficients. Well, they're all 1. They're all 1, right? They're all 1. From negative n to positive n, they're all 1. Right? And there's 0 outside. Right? Right? Okay, so that is sort of like the the dumb question. Or we could have done it directly, right, by taking the inner product of dnx against e to the ikx, right? And then we would have seen that everything's going to be 0, right? That if we're looking for the kth Fourier coefficient, we'd see that everything is going to be 0, right? All these things are going to give us 0 except for the kth one, and we would get 1 from it. Okay, so we could have done it directly or just by by looking at it. Okay, now the second one, same sort of question, right? I've got my PR theta. Maybe let's just write a PRX so it's more familiar. I've got my PRX, which is this guy. I say, well, what are the Fourier coefficients of this? Okay, and so you'd say, well, I've got to integrate this thing against e to the ikx, right, bar, right? Now, this was the non-dumb question, right? If I could pull this sum out, then I know what my answer is going to be. My answer is just going to be r to the n, r to the absolute value of n, right? But I don't know if I can pull that sum through the integral, right? Right. To get this, I need to take the integral negative pi to pi of prx e to the negative I ikx dx, right? In order to get the kth Fourier coefficient, right? So if I could slide the integral past the infinite sum, then I could just read it off just like before, right? So for that, you have to notice that this series actually converges uniformly. Okay, so exercise, this converges uniformly. Okay, and that allows you to do it. So that's what makes this a non-dumb exercise. Okay.
So that allows you to pull the PRX out?
It allows me to pull this thing out, right? So I would have this, and from negative infinity to positive infinity, r and ei and x, right? Well, if I can pull this out, I can also pull the r out. Then I'm back to this problem, right? But without that, it's not so simple, right? Okay. Okay, so yeah, one needs to use uniform convergence to get that. Okay.
What's the good things about these two kernels?
Right. So,
is it related to approximate identity?
it is actually. It is. So yeah, you asked this last time. So the Dirichlet kernel turns out not to be a good kernel. Okay. So, let's see how we should do this. Okay. Actually, I'm going to play off of your question, and then we'll close it. Okay. So, yeah. So let's think of what was good about our kernel, right? Do you remember when we were doing the proof of the Stone-Weierstrass theorem? We had this kernel Qnx, right? What was good about the kernel?
If you integrate it over R, it gives you 1.
Yeah, the integral was 1.
And if you fix any epsilon greater than 0, like outside delta is converges.
Right, right. So we had this uniform convergence condition, right? So we had this condition, we had this condition that for all delta, Qn converged to 0 uniformly.
For all x greater
Outside,
the delta goal.
yeah, outside of delta, I'm sorry, outside of x less than delta.
I think we have outside -1, 1, it just goes to 0.
So it was like this. We were integrating on some interval, right? And we said, well, outside of this interval around the origin, we have uniform convergence to the 0 function, right? So that was what's good about it. And the last thing that was good about it was that it was positive. That it was positive. So really, the condition for being a good kernel turns out to be this one: that the integral at the absolute value is bounded. Okay, but since for us it's positive, that part just follows from 1. Okay, so these are the 3 conditions of what's called a good kernel. Good kernel conditions. Okay, and as long as we have a good kernel, then what happens is that if you take your function and you convolve it with Q sub n, then
Converges uniformly back to original.
right, these guys will converge uniformly. So as long as f was continuous, then these guys converge uniformly back to f. Okay, so that was the, if you go through the Stone-Weierstrass theorem, this is the theorem that sort of generalizes out of it, right? We didn't need that particular kernel. That particular kernel was used so that we would get polynomials, right? So that we would get polynomials. But if you had any kernel, you'd still get, if you had any kernel that satisfied these conditions, then that would actually give you uniform convergence. Okay. Okay. So now, so let me sketch out how the Dirichlet kernel plays into Fourier analysis. Okay. So recall that the partial sum guy was the sum of, from negative n to positive n, of these guys. So e to the inx. Okay. These were the partial sum guys, right? It turns out that S and F is the same thing as the convolution of f with dn. Okay. Okay. But dn is not a good kernel. Okay. dn is not a good kernel. However, it's possible and so what happens is that right, SNF doesn't recover f, right? SNF doesn't recover f as you would hope, right? You'd hope that as long as you've got a continuous function, then if this thing were a good kernel, then you would just recover your function, right, uniformly. That'd be great. Okay. SNF doesn't recover f. Okay. But still, you sort of have a hope, and I don't have time to explain why you have this hope, but there's sort of a hope that you still ought to be able to recover your function. You still ought to be able to recover your function, even though this doesn't work out. And the reason is that if f and g are, so there's something called a uniqueness theorem that I was thinking to prove, but I'm no way going to be able to. If these guys are continuous functions, then they have equal coefficients, equal Fourier coefficients. Okay. Then they have equal Fourier coefficients. So you think that, well, if you know the Fourier coefficients, then you should be able to get back your function, right? You can't get it back this way, right? Doesn't necessarily, even if f is continuous. Okay. Right. So there's uniqueness then that says, well, in fact, as long as you've got continuous functions, what am I saying? What am I saying? No, not. Sorry. Let me. Yeah, sorry. So these are continuous functions, and the Fourier coefficients are the same. Then the functions agree. Well, sorry. Okay. So this is saying that basically the Fourier coefficients should be enough to give you your function back, right? But this is not the way to do it. This is not the way to do it. Okay. But so there's one initial result in this direction called the Cesaro means. Mean meaning the average, not any other kind of mean. Okay. And so what that is that you instead of taking d sub n, let f sub n So let f sub n be the sum of the Dirichlet kernels from d0 to dn minus 1. Okay, and then average it. Okay. So you take the sum of the first n Dirichlet kernels and then you average them. This is called the Fejer kernel. I don't know how to pronounce this. Fejer kernel. Okay. Now, this turns out to be, Fn turns out to be a good kernel. This thing turns out to be a good kernel. And so if you take, what does that say? That says that if you convolve this guy with f, where f is continuous, then these guys actually do allow you to recover your function. So And so this gives you some sort of analog of the Stone-Weierstrass theorem, where instead of taking polynomials, you're taking trigonometric functions. Okay, so it basically says that you can find a series of trigonometric polynomials, what are called trigonometric polynomials, that converge uniformly to any continuous function. Okay, this is like a direct analog of that. Okay. Okay, so that's one of the first things that you'll see in a course like this.